So today I'm going to talk about reinforcement learning, algorithms and application. So I am Dileep Kalathil. I am an assistant professor at the Department of Electrical and Computer Engineering at Texas A&M. I joined here around 2 years back. Before that, I was a postdoc in UC Berkeley, and before that, I did my PhD in USC. So my research area is mainly at the on reinforcement learning, especially on the theory of reinforcement learning. My PhD thesis addressed some of the fundamental problems in the context of reinforcement learning. And here in Texas A&M, I continue working on some of the more exciting ideas on reinforcement learning with my colleagues and my students. So today, in this tutorial, I will first tell you a little, give you a broader overview about what is reinforcement learning, what are the main applications as a quick introduction. Then I will go into one of the fundamental formalism that is required for addressing reinforcement learning problem, which is called Markov decision processes. And then I will briefly talk about dynamic programming algorithm. Then I will go to the core reinforcement learning algorithm like Q learning, deep Q learning, policy gradient, and deep policy gradient algorithm. And I will conclude. So today's talk is divided into two parts. The first part will be around 1 hour, 20 minutes, and then we will take a short break, and then we'll reconvene. And then the next half, I will talk about 1 hour, 30 minutes, and then we will conclude. As I mentioned before, the chat window is open. So if you have any questions, feel free to type in your question at any given time. Okay, I'll start with reinforcement learning, a short introduction. So in each subsection, I will give you the reference so that when the slides or video is available, and if you want to learn a little more, you can use these references to go back and study more in depth about reinforcement learning. So what is reinforcement learning? Before answering that question, I'm going to ask myself the question, what is machine learning? So as I mentioned in the abstract for this workshop, I'm going to assume that you are roughly there was a question in the chat window. Would you sharing the slide? I guess I'm already sharing the slides on my screen. So I guess all of you are able to see this. If you are not able to see my screen, please let me know. Oh, okay, yes. After the talk, I will share my slides as a PDF. Yes, I will do that. Okay, so before answering what is the question on what is reinforcement learning, first let me ask the question myself, what is machine learning? And I'm assuming that all of you are familiar with the idea of machine learning some way or the other. Some of you may have already taken the course, and or many of you may be using machine learning as a part of your research. Okay? So those who are even vaguely familiar about machine learning knows that machine learning can be classified broadly into three main classes: unsupervised learning, supervised learning, and reinforcement learning. And if you are familiar with machine learning, you are very likely to be familiar with the first two classes of machine learning, unsupervised learning and supervised learning. So what is unsupervised learning? If you are like me, if I don't know a keyword, I'll first Google it, and then I will go to Wikipedia and say what Wikipedia says about that. Of course, when I do research, I will go to the more authentic resources like a textbook or paper, but my first resource is always Wikipedia. So the Wikipedia says that unsupervised machine learning is a machine learning task of inferring a function that describes the structure of unlabeled data. So you are given a set of data without any labels. You essentially want to use some kind of intelligent machine learning based algorithm to say something more about the structure of the data. The very famous examples of unsupervised learning is, of course, clustering and other dimensionality reduction techniques like PCA, metric completion, image painting, collaborative filtering, etc. So this is a very familiar application of unsupervised learning. You are given a two-dimensional data points. So this is the scatter plot of the data. Your goal is to say something more about the structure of the data. Probably you want to classify this data into different clusters. So by looking at it, you can roughly identify one or maybe roughly identify 2 or maybe 3 clusters. So you use some algorithms like k-mean or k-mean plus algorithm to come up with a clustering of this data points. I think most of you may be familiar with this. So unsupervised learning can be thought as some kind of descriptive analysis, that essentially means that we are interested in summarizing the data in a way to make it more interpretable. So that is one of the first main class of machine learning. The second main class of machine learning is supervised learning. It is clear that if you are some way familiar with machine learning, you know about supervised learning. So supervised learning is essentially the task of learning a function that maps an input to an output based on the input-output pair. So you are given a set of data with the correct labels, and you want to learn using machine learning algorithm, a function which is typically a classifier, so that if you are given a new data point, you can classify to the correct class. The most famous example of supervised learning or the application area is image classification. You can use it for handwriting recognition, email spam filtering, face recognition, speech recognition, etc. So typically when I think about machine learning, or I tell my student what machine learning, or especially supervised learning is, I give this example of image classification, essentially identifying cats versus dogs. So this is the, you are given a set of training data. This is an example from CPART training data. And then you learn a classifier, probably using neural network. And the goal is that if you are given a new set of data points, like for example, you have a new testing data, that is this cat image, you want your classifier to tell what is in that image. In this particular example, that's a cat. Supervised learning is useful not only for classification, it is useful for many other applications like face recognition, spam filtering, digit recognition, Siri. And we know that this is one of the most successful application of machine learning in the last five years or so, after 2012, where people realized that deep neural network can be used to do like a very successful image classification. This is one example that I really liked. This is like a screenshot from Facebook from July 2019. There was a worldwide outage of Facebook service around that time. So people logged into Facebook were not able to load the image, but they were only able to see something like this. If you look at this image, the image was not loading, but you see that Facebook used some kind of supervised learning algorithm to identify what is in that image. Here you can see that the Facebook label given to that image is, that image contains trees, sky, outdoor, and nature. And this is just one example of how these big data companies are using supervised learning. There are many other successful examples of supervised learning. So you can think supervised learning as some kind of predictive analysis that aims to estimate output from the current data. Essentially, you are coming up with a good function using your neural network so that you can estimate, you can make some prediction about the current data based on the data given to you, based on the labeled data given to you. What is reinforcement learning? So I used my same methodology, that is, I went to Wikipedia, checked the definition of reinforcement learning, but reinforcement learning definition of Wikipedia is much larger or bigger than the definition of supervised learning and unsupervised learning. Wikipedia suggests that reinforcement learning is an area of machine learning concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. The problem, due to its generality, is studied in many other disciplines such as game theory, control theory, operation research, information theory, optimization, multi-agent systems, swarm intelligence, and many more. So I also found this interesting Venn diagram representing the position of reinforcement learning with respect to other areas like mathematics, economics, psychology, neuroscience, engineering, machine learning, etc. So this is a larger picture of reinforcement learning from a different perspective. Today's lecture, I am going to view reinforcement learning as a class of machine learning and I'm going to give you algorithms and theory and algorithms of reinforcement learning from that perspective. So what is reinforcement learning? Reinforcement learning, there are two main entities we call agent and the environment. The agent, you can think it as yourself or the algorithm that you're trying to learn, the algorithm that you're designing. The agent gets an observation about the state of the world. Based on the observation and based on the algorithm what we have or the agent has, the agent takes an action, control action. That control action influences the state of the world. Depending on the state of the world and the control action, the agent will receive a reward, and that will change the observation again. So roughly the sequence will be like this. At each time step, the agent will select an action AT. The agent will receive a reward RT. Then based on the control action, the state of the world will change. You will get a new observation. And the environment acts in kind of a reverse order. That is, environment will receive an action AT from the agent. It will emit a reward and it will emit an observation, and then it will go on. So clearly you can see that reinforcement learning addresses a problem where there is a sequential interaction between the agent and environment. Okay? To give you a more concrete setting, think yourself as playing a video game. The action is essentially the joystick position that you are going to take. The reward is obviously the reward that you are getting, that the reward is displayed on the screen. The observation is essentially the state of the game that you see on the computer screen. So depending on the state of the world or the observation, you see that observation, you take a control action, you move the joystick, and then you get a reward. And then your control action obviously is affecting the state of the world. For example, if you want to destroy those dragons by firing bullets, some dragons will get destroyed, and then the state of the world will change to something else. So where is reinforcement learning comes here? So clearly, if you are playing this game, Atari game, you know something about the game and you have a rough idea of how to play the game. Probably somebody taught you, or you taught from your human experience, and then you know the rules of the game. And then you know the rules of the game so that you can take appropriate control action to maximize the reward that you're getting, or you want to win the game. Reinforcement learning comes here. Assume that you don't know anything about the game. The rules of the games are unknown. It is like the algorithm that you are designing. Rather than telling the algorithm that these are the rules of the game, these are going to be the optimal strategies, and this is how you want to play, you want to come up with a machine learning based algorithm that doesn't know anything about the rules of the game or anything about the observation sequence that it is going to get. But at the same time, you want to design an algorithm that can win the game or maximize the reward that you can get from the game. So that is where reinforcement learning comes from. The algorithm which will help you, the class of algorithm which will help you to achieve these objectives is essentially coming from the class of algorithm from reinforcement learning. So why reinforcement learning is different from the other two classes of machine learning algorithm, like supervised learning algorithm and unsupervised learning algorithm? Obviously, from this example, you notice that reinforcement learning is essentially learning to make a sequence of optimal decisions. So the one important keyword here is that you are taking a sequence of optimal decision, and especially the next stage of the world may be uncertain. There may be some stochastic dynamics involved. In supervised learning and unsupervised learning, this idea of sequence of decision is absent. Think about you are designing like a neural network based classifier, and then you are giving testing data one after the other. First test data is an image of a cat, and the neural network is telling you that that's an image of the cat. Second data point is essentially an image of the dog, and the neural network will tell you that is an image of a dog. So there is no explicit connection between the decision taken at one time step to the decision taken at another time step. So the difficult aspect of the sequential nature is completely absent in the supervised learning algorithm. And obviously you can see that that idea of sequential decision making is absent in the unsupervised learning also. But reinforcement learning, that is crucial. If you think about the broader definition of AI, we want to design like a robot or an artificial intelligent algorithm that can take good action, optimal action in a real world. So essentially, if you want to develop an algorithm to achieve that objective, reinforcement learning is going to be the tools that you're going to use. So some more salient points are, in reinforcement learning, there is no supervisor. You are only seeing the stage of the world and the reward signal. So unlike supervised learning, where you are given a set of data in image classification that is typically megabytes, terabytes, or even gigabytes and terabytes of data with labeled data. You are getting a large amount of data with thousands of images of cats, dogs with correct labels, and you are using that supervised data with correct label to train a neural network. But in RL, there is no supervisor telling you this is the optimal action to take. So you need to learn by experimenting. And this feedback that you are getting, the rewards and observation, need not be instantaneous. So that may be delayed. That will affect the speed at which you learn. Clearly, as we mentioned, there is a sequential decision-making nature involved. And actions may have long-term consequences. So clearly, you cannot take greedy action all the time, because the action that you're taking may affect you or may affect your reward after next time step or the next time step or many time steps after. Think about you are investing in stock market. Probably this is probably not the immediate time to invest in stock market because stocks are down. But if you think in terms of long term, probably if you invest a little bit of money now and when the stocks are up, probably that is a useful action that you are currently doing. Clearly that is not a greedy action that will not benefit you tomorrow, but that can benefit you like maybe after many months, hopefully, if not years. Then another example, silly example that I will give in classes, if you are preparing for the exam, clearly preparing for an exam every day is a boring task, but preparing an exam one day before the exam is also like probably not a very pleasant task. So investing time for studying for the exam now may be useful in the future. Another big issue with reinforcement learning, because of the sequential nature, is that the data that you are getting is IAD, not IAD. Because every time when the agent is taking an action, then that is influencing the state of the world, that is influencing the observation. So due to the sequential nature, the data is clearly non-IAD. Most machine learning algorithm works under the assumption that the data that they are receiving is IAD. So that is clearly different here. And another crucial aspect is that nobody is giving you a set of data. If you think about that, is going to be the most stark difference between the two other class of machine learning algorithm and reinforcement learning algorithm, where in supervised learning and unsupervised learning, somebody is giving you a set of data, but here there is no data given to you a priori. The agent has to learn by experimenting with the environment. So it is the agent who generates the data. So what can RL do? So I'm going to give you two examples on like some interesting application of RL, not really an application, but useful thing that RL can do in a lab setting, not in an industrial setting. The first one is from a paper by Peter Abel, Coates, Quigley, and Andrew from Stanford. As you have seen, this is from a university research group. They developed like a reinforcement learning algorithm for doing an aerobatic helicopter flight. Clearly, I mean, I don't need to belabor the point, but still, clearly you can see that this is not a supervised learning application or unsupervised learning application. That helicopter needs to take a sequence of control action, and that can be done by the class of reinforcement learning. I'll give you one more example, very recent, from the company OpenAI. They developed this robotic hand. So this is like a robotic hand which can solve the Rubik cubes. Solving Rubik cubes, writing a code to solve Rubik cube is not difficult at all. It is very, very standard. The interesting fact about it is that with one hand, the control action is designed appropriately so that it can go from one position to another position. Okay? So they demonstrated is reasonably successful, not completely success, because a lot of time the robots drop the Rubik cube, or sometimes it gets stuck. But still, you can see that this is not an easy task. Even for humans, doing this control task with one hand is a very difficult thing. And especially correctly giving the actuation required to kind of turn this in multiple directions at the same time is no small feat at all. And this is also achieved by reinforcement learning. So I can go on giving example, but the interest of the time, I will skip I'll skip all this example and then come back to our main point. That is, so what is reinforcement learning? So reinforcement learning, you can think it as a prescriptive analysis. It's not a descriptive analysis, or it's not a predictive analysis. It is a prescriptive analysis. What is prescriptive analysis? Essentially, it is telling you to take action in such a way that it will get you guaranteed outcome that you expect the algorithm needs to do. Okay? So to get this kind of prescriptive analytics or prescriptive algorithm, reinforcement learning is the class of algorithm that you want to use. One very important aspect of reinforcement learning, which is again not in classical machine learning algorithm like supervised learning and unsupervised learning, is exploration versus exploitation trade-off. So as I mentioned before, in reinforcement learning, you are not given any set of data. That is one of the biggest difference between supervised learning and unsupervised learning. But you know that any kind of machine learning requires some kind of data. So where do they get the data from? Where do we get the data for reinforcement learning? So agent needs to generate its own data. So agent, how does it generate the data? By interacting with the environment. So you can think of RL in some way, a trial and error learning, but not a completely trial and error, like not a random trial and error, but a very highly intelligent, carefully designed trial and error learning. So the goal is to come up with a good control policy that is from its experience of the environment, but without losing too much reward along the way. So this is actually an online decision making. At any given time, the control agent has to take a decision. So such online decision making problem typically involves two choices. One is the choice of exploitation. That is, you may want to take the best decision given the current information. The other is exploration, that the algorithm may want to gather more information by taking some action that may not be optimal if you are thinking only about the rewards, but it may be really good to gather information. So that long-term strategy may involve suboptimal short-term decision. Think about your playing chess. You don't want to always greedily kind of take the other player's action. You may want to measure how good the other player is. So you want to take some exploratory move and see what is the situation. And then you want to come up with an optimal strategy to beat your opponent. So think about this as an exploitation versus exploration trade-off. And how do we balance this exploration and exploitation is a fundamental core issue in reinforcement learning. To give you like a more stylistic example of exploration exploitation, think about restaurant selection. Exploitation is, of course, go to your favorite restaurant, and exploration is trying a new restaurant. Online advertisement, from the perspective of, say, Google AdSense, exploitation is essentially showing the most successful ad, but humans have different preferences. So Google wants to understand, or Amazon wants to understand your preference. So they may want to show you a different ad and see whether you are clicking it or not. And that is essentially a way to explore your taste or preferences. Oil drilling. In fact, this term probably came from the exploitation, essentially drilling at the best known location. Exploration is drilling at the new location. And as I mentioned, if you are playing chess, exploitation is essentially playing the move you believe is the best, and exploration is playing an experimental move. Okay. So with that, I will conclude my quick introduction to reinforcement learning. So what is reinforcement learning problem? The agent doesn't know how the environment works. An agent has to interact with the environment to learn. An agent gets two feedback. It can observe the state of the environment at each step. It gets a reward at each step. And then agent goal is to learn a control policy in such a way that the agent or the reinforcement learning algorithm want to select action sequentially. And the objective is to win the game if it is a game, or more mathematically in a correct way, the agent's objective is to maximize the expected cumulative reward. So this is the reinforcement learning problem in a more qualitative sense. Now we are going to make it precise in terms of a mathematical formalism called Markov decision processes. I'll take like a half a minute pause here, and if you have any questions, please type in the chat. Okay, so I will continue now. Let's see in the chat. Oh, thank you. Okay, so excuse me. Okay, so we just saw the qualitative description of reinforcement learning, but we know that we are engineers and probably we consider ourselves as applied mathematicians also. So we know that qualitative description about a process is not enough to come up with interesting algorithm or interesting insight about the problem. So like engineers, given like a real world problem, rather than trying to solve it in the real world, we want to come up with a mathematical model for that real world problem, and then try to bring our mathematical tools or algorithmic insight to solve that mathematical model, then come up with a solution for that and transfer it back to the real world. So our goal in this, in the reinforcement learning scenario is come up with an optimal control policy that will solve a real world control problem. So we are going to come up with a mathematical formalism that will take a that will take a real world control problem and convert into a mathematical formalism. And that mathematical formalism we are going to use is called Markov decision processes. I know that many of you may be familiar with Markov decision processes, but some attendees are not. So since Markov decision processes is at the core of reinforcement learning, I'm going to spend next many slides on giving the introduction to Markov decision processes and some basic algorithm to solve Markov decision processes. Some figures for this part is taken from a UC Berkeley course with the permission of the instructor. So I'm going to give an introduction to Markov decision process using this particular example of a grid world. As the figure suggests, your goal is to come up with a control policy to navigate this robot on the grid in the grid world. So there is a starting point, and the robot can move along this grid world. So this is actually an obstacle. So the robot cannot go into that square. This is essentially the target that agent wants to go. And when the agent reaches there, the robot reaches there, it will receive a reward of +1. And this is something that agent really shouldn't go, doesn't want to go, because if the agent falls into that square, then it will get a reward of -1. So we assume that the agent lives in a grid world, and we are going to assume that the world is non-deterministic. So there may be inherent uncertainties in the environment, and action don't go always as planned. This is typical in most of the control system that we work on. Think about you are coming up with a control algorithm for like a drone, but if there is wind in the environment, and when you are flying the drone, and if you are taking a control action for the drone to move forward, but the wind is at perpendicular direction, we know that the next step of the drone is not exactly in that move forward. It may kind of drift a bit. So there may be many uncertainties in communication systems or in chemical process plant. There may be noise, and you can think about many stochastic uncertainties as a part of the real world. So to model this correctly, we are going to assume that the real world is non-deterministic. In particular, in this example, we are going to assume that if the robot takes an action to go forward, it will go forward and it will reach the next forward state with a probability 0.8. But with a probability 0.1, it may shift to the right, and with a probability 0.1, it may shift to the left. We are going to assume that agent is going to receive a reward at each time step, and the reward will depend on the current state and action. Clearly, it will depend on the current state, because as we mentioned, if the agent reaches this point, it is going to get a reward -1, here +1. And you can think about the scenarios when the reward will depend on the action. For example, if you are again think about a control algorithm that you are developing for flying a drone, and you don't want to spend all the battery of the drone by like making high energy control action all the time, because you may have to go deliver something and come back. So you want to store enough battery for doing that. If you are developing autonomous car or like a driving algorithm for racing, you don't want to spend all the fuel, because you want to minimize the fuel consumption, still achieving the objective. So we are going to model this as something called Markov decision processes. We assume that there is a set of states. Here, the natural representation of the state is the position of this robot. So here, each rectangle can be thought as a state of the world, and essentially the position of the robot is that what we are considering the state of the world. We have a set of action. Robot can take 4 different actions at each time: up, down, left, right. And there is a transition function. This is represented as a probability. So P of x prime xa is essentially the probability of moving from the state x to state x prime if the action A is taken. Okay? So if the agent is here, and if the action go forward is taken, then we know that this probability to go here, reaching this particular state is 0.8, reaching this particular state is 0.1, and reaching this particular state is 0.1. And similarly, if the agent is here and takes an action forward, reaching this particular state is 0. So similarly, you can assign a probability of the agent moving to a given state from any other state by taking any other action. That is essentially called the transition probability function. This is, if you think about this, this is nothing but the model or dynamics of the control system. If you have taken any linear control system, this is nothing but x of t plus 1 is equal to a of x of t plus but plus wt. I'm not going to explain this term, but if you have taken a linear control system class, you know this is the dynamics of the system, where wt is the uncertainty. And I mentioned about the reward function, and the reward will depend on the state and the action. In some formalism, you will see that the reward will depend on the current state, current action, and the next state. But this is the formalism that you typically see. The reward will depend on the current state and current action. And typically in this problem, you have a starting state and a terminal state. And this is a very useful model for approximating the real world systems. So we just introduced like a basic formalism for Markov decision processes. So the idea of decision is clear because agents are taking a decision. Process is because you are taking a sequence of action. What is Markov here? What is Markov doing here? So a Markov property generally means that given the present, the future and the past are independent. What do we mean by that? Consider the probability that the next state is small xt plus 1. Given the entire history starting from the time step 0, action state at time step 0, action at time step 0, all the way up to state at time t and action at time t. And if a system has Markov property, it essentially means that the history is not really relevant. All you need to think about the probability of being in the state xt plus 1 in the next time step will only depend on the current state and the current action. So this is nothing but the transition probability function that we just defined. So essentially, Markov property means that if you know the current state and current action, history is irrelevant to predict the future state. Okay. Is the world really Markov? Well, not always. You can come up with like very kind of convoluted example of the world. The next state depends on the current state as well as the previous state as well as the previous state. There is a trivial way to make almost all control problems to a Markov problem because you can assume that the current state not only include the current state but the previous state and the previous state and the previous state. So you can treat your history itself as the current state, but that is not really a useful formalism. But you see that in most control problem, considering the next state will depend only on the current state and current action is good enough to come up with good approximation. So this is the standard approximation that we take in control theory. And we know that this is a very useful assumption for modeling a large class of real world problems. So why do you think this is useful? It's obviously useful because since you are not storing the entire memory or entire history, that will give you a tremendous reduction in the memory required to solve the Markov decision processes and the computation required to solve MDP. This is because if you are storing the entire history, the set of all possibilities will explode with time. That will increase exponentially with the time. So the required memory is will increase exponentially with the time, which is something that we don't want. So with this Markov property, we can tackle this control problem very efficiently. So you can think about like examples like this is from my class homeworks. Like you can think about controlling a lunar lander. Here I don't have a good control policy, it is crashing, but that can be modeled as a MDP. Inverted pendulum, card pole, all of this can be modeled as an MDP. Some interesting robotic examples or the problem video that I showed you before, all of them can be modeled as an MDP. Give me a moment. Okay, so now let me give you a little more formal definition of MDP. MDP is a tuple with X. It's a tuple with a finite set of states, a finite set of action, a transition probability matrix, and a reward function. You can think about MDPs with infinite set of states and infinite set of actions. That is entirely feasible, possible, but for mathematical tractability and ease of exposure, I'm going to consider only MDPs with finite set of states and finite set of action. Okay, given now we have a formalism. That is, what do we have now? If you are given any real world control problem, we know an approach to take that real world control problem, model it mathematically using the formalism of MDP. Good, so far good. But what is our real goal? Our real goal is to come up with a control policy. So what is a control policy? A control policy specifies what is the action to take given the current state of the system. So the control policy can be deterministic or stochastic. What do we mean by stochastic control policy? So phi of A given X is the probability that you are going to take the action A if you are in state X. So phi of A given X is defined as probability of the action at time T is A given your current state XT is X. So you can take it make it deterministic also, assuming that you deterministically take only one action, and the probability of every other action is 0. Now, a policy will fully define the behavior of an agent. Once you don't even need to think about the reward or like environment, because if you already decide that this is the policy that the control agent is going to take, for example, think about like developing like a control policy for an autonomous car or a toy car. If the control policy is always go forward, you know that irrespective of the reward, the agent is going to follow the control policy, which is always go forward. And that essentially fully defines the behavior of the agent. Good. Now we define what is a control policy, but our real goal is not to come up with an arbitrary control policy. We want to come up with the best control policy. Think about like a drone, developing a control policy for a drone. You want the drone to deliver a packet from one point to another point. So the drone needs to pick up the packet, find an optimal path from one point to another point, deliver that packet and come back. And you want to do in the most efficient way. That is, you want to minimize the cost for running this operation. So you can think about many control policies. For this problem, clearly always going straight is not going to be a good control policy. So how do we compare two different control policies? What is a metric or what is a number that you're going to use to compare the two different control policies? That is called the value of the policy. So the value of the policy is defined in the following way. That is, value of the policy evaluated at state X is the expected cumulative discounted rewards obtained by taking action according to that policy starting from X. So the value of the policy phi for the evaluated state X is defined like this. Assume that your initial state is X. And assume that you are taking control action according to the policy phi. Then first step, you will get a reward. Second step, you will get another reward. Third step, you will get a reward. You just want to sum up, take the cumulative sum of the reward. But you don't want to take the cumulative sum by itself due to multiple reasons. Mathematical tractability is just one, but there is other psychological and more reasonable reason for that. But you want to add a discount factor gamma. Gamma is a number between 0 and 1. So instead of taking the cumulative reward, you want to take the cumulative discounted reward of following the policy, that is taking the control action according to the policy phi by starting at the state X. That is known as the value of the policy. So clearly, I mean, this is a toy example. Here you have a policy that is always goes right and always go forward. Clearly from the pictorial definition, you can guess that this is going to be a very bad policy and this is going to be a good policy. Okay, so this is essentially the value of the policy marked on that grid world problem. You can see that the values corresponding to this policy is much higher than the values corresponding to this policy. Okay, now we have the formalism called MDP, Markov decision processes, to take any real world control problem and convert that into a mathematical model. And we know what are we looking for? We are looking for a control policy in such a way that you want to maximize the value corresponding to that policy. Now, what are the mathematical questions that we are going to address? So we are going to address three major or most important questions in this framework. The first question is, how do we evaluate the policy? We just define what is the value of the policy that is given as an infinite sum clearly and with an expectation. So the expectation is with respect to the randomness inside the bracket. You see that this is an infinite number of random variables. So this is going to be a very difficult expectation to evaluate if you want to take the integrals and evaluate. So there should be an easier way to do this. So our first question is, how do we evaluate a policy? But we know that that is not the real question that we want to get. We essentially want to compute a value function such that you essentially want to compute something called an optimal value function, which I am defining the following way. V star, the optimal value function, is the best value function in a way. For each policy, you have a value V pi. So you want to find the value function with respect to all the policies. So you want to select the best value function corresponding to the best policy, and you are going to define that as the optimal value function. So this is the second question that we are going to address. How do we compute the optimal value function? Well, that is a stepping stone towards the basic problem that we are trying to understand. That is our real goal. Think about all the examples that we worked out in the grid world. You want to come up with a problem. You want to come up with a policy so that you can navigate the robots from one end to the destination. Drone example, autonomous driving example, everywhere. Your real goal is to come up with an optimal control policy. That is, the pi star is argmax of p pi. That is the policy that will give you the best value function. In today's lecture, I will not discuss about this. I will tell you how to compute the optimal value function and how you can use that optimal value function to compute the optimal policy. So we are going to answer the question of how do we compute the optimal value function first. This question. Let me emphasize, V star is something that we call optimal value function in such a way that is the best value function that we can come up with. That is a value function corresponding to the best policy. How are we going to compute it? We are going to make an important property of the optimal value functions called Bellman optimality equation. Okay? Let me first state the property, then I will explain the intuition behind that. Suppose V star is the optimal value function. Then Bellman optimality equation or this Bellman property says that if V star is optimal value function, then V star satisfies this equation. Okay. What is that equation? The value corresponding to the state X is given by what is on the right hand side. Inside the parenthesis, you have the reward corresponding to the current state and current action plus gamma times summation over y, next state, p of y given xa, v star of y. So if you think about this term is nothing but the expected value corresponding to the next stage. So inside the parenthesis, what you have is the reward corresponding to the current state and current action plus gamma times expected value corresponding to the next stage. But here you have already fixed an action. But suppose if you take the best action in a way, that is a maximum over action, then that should be equal to the value corresponding to this stage. Okay. What is the intuition? Think about the following scenario. Assume that V star is the optimal value function. Now suppose that you are at the state X. Okay. You are in the state X. And now suppose that you take an arbitrary action A. You know that the environment is stochastic. So with some probability, you may end up in state Y1, and some probability you may end up in state Y2. Okay. Now assume that from the next step onwards, that is from Y1 onwards, you are going to follow the optimal policy. Okay. So what is the value corresponding to the state Y1? Because by definition, since you are going to follow the optimal policy from Y1, the expected cumulative discounted reward that you will get by starting from Y1 is going to be V star of Y1. Similarly, the value corresponding to Y2, assuming that you are going to follow optimal policy from Y2, is going to be V star of Y2. Okay. So then, what is the value corresponding to the state X given that you are taking the action A? That is going to be this. So the value corresponding to the state X by taking an action A is, if you are in the state X and if you take an action A, then you will get a reward R of XA, right? Then you are going to the next stage. Then for the next state, there will be the value corresponding to the optimal value function. But the next state is random. So instead of calculating the exact value, you want to calculate an expected value there. So the value corresponding to the state X by taking an action A is the current value plus gamma times the expected value corresponding to the next state. So this is the value corresponding to the state Y, and then you want to multiply the probability of being in the state Y given that you are in the state X and you take an action A, and then you want to sum it over all possible state. That is nothing but the expected value of the next stage. So current reward plus gamma, because you want to include the discount factor of the gamma time expected value of the next state, is going to be the value corresponding to state X and action A. But now you already know that you don't want to take any arbitrary action, because if you want to get the best value, you want to take the best action. So rather than taking an arbitrary action A, you want to take the best action by putting the max over A. You want to take the best action. But then, given that you are taking the best action at the state X, and given that you are following the optimal policy from the next state onwards, then you should be getting the optimal value in the state X also. But the optimal value in the state X is V star of X. So whatever you are given on the right hand side, and then you are taking the max with respect to A, that should give you the optimal value corresponding to the state X. So that is the intuition for this Bellman optimality equation. Okay. So we are going to make use of this intuitive equation or the property called Bellman optimality equation to compute the optimal value function. So we are going to make use of Bellman optimality equation for defining a mapping called Bellman operator. Bellman operator is nothing but a mapping T, which I'm going to denote by the mapping T, from an nx dimensional vector to an nx dimensional vector space to an nx dimensional vector space. Nx is the dimension of the number of states in the system. Okay. So the idea is that if you are giving V as the input to the Bellman operator and evaluated for the state X, this is the X dimension, that function is defined like this. You see that this is essentially the same definition as before, but instead of V star, you are giving any argument as V. So treat this as a function. I'm going to call it a function, mapping, or operator interchangeably. Okay. So this is called, the function that I defined, T, is called Bellman operator or Bellman function. Now, coming back to our question, we want to compute the optimal value function. I'm going to define an approach called value iteration using this Bellman operator. I'm going to define an iteration like this: Vk plus 1 is Tvk. That is, you take the current value Vk, you get the output Vk plus 1, you put it back to T, you'll get Vk plus 1. So as a result of this iteration, you will get a sequence V0, V1, V2 up to like Vk, Vk plus 1, Vk plus 2, etc. So I'm proposing this as an approach to compute the optimal value, and this approach is called value iteration. There are many questions now you can ask. This approach that I just proposed, will it converge? And even if it is converging, it is not obvious that it will converge the optimal value function. So will it converge the optimal value function? And now, but we started by saying that there is something called optimal value function. Is it unique? Will it depend on your initial condition? Will it depend on how you define the policies? So what is the guarantee that it is converging to the value function that you want to converge to? And how fast does it converge? Okay. So we are going to answer all this question, not very rigorously, but I will try to give you an intuitive explanation for all of this. And obviously, our main goal is to compute the optimal policy from the optimal value function. Okay. To argue this a little more systematically, so that the value iteration that I just proposed will converge the optimal value function, I'm going to define another notion called fixed point of a function. Most of you may be familiar with this idea. Suppose you have a function from a space to itself. We say that x star is a fixed point of that function if f of x star is equal to x star. That is, the function is not changing that value. F of x star is equal to x star. Okay. So in two-dimensional, it is very easy to visualize. I have a function y is equal to f of x. To compute the fixed point of this function, all you need to do is kind of draw a line, 45-degree line, and at the point where the 45-degree line intersect with the function, those points have to be a fixed point of the function, right? So think about this point. This is, say, sum x1. Clearly, since this function is intersecting with the 45-degree line, We know that f of x1 is equal to x1. So x1 is a fixed point according to the definition. And it has multiple fixed points. We are going to observe that, or the first claim is that v star, our optimal value function, is a fixed point of the Bellman operator T. There's nothing very mathematically deep about this. It is because just the way we are defining Bellman operator and Bellman optimality equation. Remember, this is how we define Bellman operator as a function. Given any v, you can compute the output of that function. But we know that according to Bellman optimality equation, according to that intuition that we developed, the optimal value function satisfies this equation. Now, all you need to see is compare these two equations. Consider you are giving v star as the input to the Bellman operator. Then this is how you evaluate. And by definition, that is going to be exactly v star. So given that the Bellman optimality equation exists and then that is satisfied, and this is how you define Bellman operator, this observation is very straightforward. V star is a fixed point of the Bellman operator. Good. Why this is useful? But now essentially it is useful because now computing the optimal value function, remember optimal value function has a very precise physical meaning, that is the value corresponding to the best policy. But we kind of got rid of those physical intuition. We converted this into a mathematical problem. What is a mathematical problem now? We have something called a Bellman operator, and the optimal value function is essentially the fixed point of the Bellman operator. So then at our hand, we have a very precisely stated mathematical problem. The optimal value function is nothing but the fixed point of the Bellman operator. So computing the optimal value function is nothing but computing the fixed point of the Bellman operator. So we took the real world problem, did some mathematical modeling, and now we are going to compute the fixed point of a function which we call Bellman operator. Okay. How are we going to do that? In general, computing the fixed point of a function, especially in high dimension, is going to be a very, very difficult task. But there is something that will save us here, which is called a property of the Bellman operator called contraction mapping. Okay. So I'm going to make a claim. I'm not going to prove this, but I'm going to argue that the Bellman operator T is a contraction mapping. That is, what is contraction mapping? Consider two vectors, v1 and v2. Think this as two value function. Assuming that you are taking the Bellman operator, give the v1 as the input to the Bellman operator and v2 as the input to the Bellman operator. So the norm of the norm of tv1 minus tv2 is going to be less than or equal to norm of v1 minus v2. That is, distance between v1 and v2 before and after operating it with respect to the Bellman operator. The distance after the Bellman operator is going to be strictly less than the distance before the Bellman operator. So in a way, you are kind of contracting there's some kind of contraction property happening. Think about this as like v1 from the space, v2. This is the distance between v1 and v2. Now you map this to that space itself by taking by using the function t or the operator t. This is your tv2, and this is the distance between tv1 and tv2. As the figure indicate, this distance is less than this distance. Strictly less than, because the number gamma, discount factor, is going to be less than 1. So that is the contraction property that we are talking about. You compare the distance between two vectors before and after operation, and if you can argue that the distance has reduced strictly, then we say that that operator is a contraction operator. Why that is useful? Then if a function is contraction, if an operator is contraction, or if a mapping is a contraction mapping, then you can prove very nice properties about that function. First thing is that you can prove that that function will have a unique fixed point. In this case, we know that it has a unique fixed point, which is optimal value function. But we will also know that if you do an iteration using that function, that will converge to the unique fixed point, which is not true for general function. It is true only for contraction mapping. It is very easy to observe that. Think about our value function iterate. Consider the distance between vk plus 1 and v star. Remember, we are doing value iteration. Our goal is, our hope is that vk will converge to v star. So the distance between vk and v star will reduce to 0. Let's see how that is happening. So consider the k plus 1 iterate, vk plus 1 and v star. By definition of value iteration, vk plus 1 is going to be, this has to be equality. So by definition of vk plus 1, vk plus 1 is nothing but tvk by definition of value iteration. Now v star is a fixed point, so I can write v star as tv star. So norm of vk plus 1 minus v star is same as tvk minus tv star. But now I know that t is a contraction mapping, so this is less than or equal to vk minus v star. Now I got a vk minus v star. Then I can write it in terms of vk minus 1, the norm of vk minus 1 v star, and I can do this iteration, and then after k plus 1 step, I'll get this equation. That is, after k plus 1 step, I can argue that the distance between vk plus 1 and v star, the norm of vk plus 1 minus v star, is going to be less than or equal to gamma power k plus 1 and the norm of v naught minus v star. What does it mean? The v naught minus v star, assume that that is a bound, that is a finite number. The gamma is a discount factor which is less than 1. So as k tends to infinity, this quantity is going to 0, which is means that your RHS is going to 0, which means that your LHS will go to 0, which means that your Vk will converge to V star. So this is the claim that essentially this is kind of a weak argument saying that the value iteration that we introduce for computing the optimal value function will indeed converge to the optimal value function as we expected. And that property that is happening because the way that we are defining the value function using the Bellman operator. I'm not going to further technical details of this, but if you happen to read any work on any research paper on reinforcement learning, this is one of the basic formalism that you will see. And most reinforcement learning, surprisingly, is trying to understand this operation, how the Bellman operator works, especially in very, very large dimension, especially with neural network. So I thought that it is, I know that there's a little more technical depths than we can typically go in like a quick tutorial, but I want to emphasize that since this is the core material for reinforcement learning, I wanted to introduce this. Okay. One more very quick intuitive idea how this fixed point works. So assume that, think about like in, this is in one dimension. The green curve is essentially your t function, and x-axis is j, any arbitrary value. This is the t function, and you want to write draw a 45-degree line which will intersect with this function, and that is your fixed point, which is your optimal value function. So you can start at some point v, then you get tv, then you want to project it back to x-axis, then apply the function again, you get t square, then you want to project it back to x-axis, apply the function again, t cube, and then you want to project it back to x-axis, then you apply the function again, and you can see that as time progress, you will slowly converge to this fixed point. So let me quickly summarize what we just discussed so far. Our goal is computing the value function v star, and the optimal value function satisfies the Bellman optimality equation. And Bellman optimality equation, the optimal value function is also the unique fixed point of the Bellman operator. And how do we compute this? We can compute this by an approach called value iteration, that you take the Bellman operator and iterate by making an initial guess, and that will converge the optimal value function. I'll take a half a minute pause here. If you have any question, let me know. There's a question from Henry Ruiz. Given a task, there is any methodology to identify the inputs I should give to my agent to learn successfully the task? Little confused about the question. Are you assuming that how do we come up with the state space representation or the reward representation? If that is the question, yes, that is an engineering design problem. Essentially, it seems that you're asking, given a real world problem, how do you use the MDP formalism to convert into like a mathematical model? That's an engineering modeling problem. Yes, there are ways to do. You can entirely avoid the idea of reward design by using something called imitation learning. Since that is like a completely different topic, I would like we can chat about that offline. But here, my interest for this this short tutorial is assuming that somebody has already done the modeling. That is, you have an MDP formalism. You are interested in solving that MDP, or in reinforcement learning scenario, you are interested in coming up with learning the optimal control policy if you don't know the model. So I'm assuming that some kind of state representation and reward representation is given to you. Okay, let me continue. So quick description of value iteration. So given the grid world example, you can start with all 0 values and you do value iteration, and you see that after 10 iteration or so, it is converged. 10 iteration, this is the value. 11 iteration, even after 100 iteration, there's no much change, which essentially means that by 10 iteration, you have converged. I want to quickly introduce another function called Q function. With anticipation that we are going to discuss Q learning very short. So we know what is value of a policy. That is the expected cumulative discounted reward that you obtain by starting from the state X and following the policy pi. We are going to introduce another terminology called Q value of the policy. It's almost like the value function, but you are going to define the Q value not only for a state, but for every state and every action. So there's a slight difference. Expected cumulative discounted reward obtained by starting from the state X and taking an action A that need not be the optimal action. So think about you are in the state X, you take an arbitrary action A, but then onwards you are going to follow the policy pi. What is the value that you are going to get? That value is going to be called Q value. Why are we interested in Q value? We will discuss about that very soon, because the intuitive idea is that if you know the Q value, it is very easy to compute the policy. Okay. Now, just like we defined the value and optimal value, it is easy to define the, excuse me. Just like we defined the value and optimal value, it is easy to define the optimal value, Q value and optimal Q value. So optimal Q value is defined like this. Optimal Q value function is given the stage X and action A, this is the reward that you are going to get. But from the next time step onward, you are going to follow the optimal policy. So the value corresponding to that is V star, and combining that, you will get Q star. So this also indicates that given the V star, given the optimal value, you can convert it back to the optimal Q value. So given V star, we know how to compute the optimal Q function. Now, given Q star, how do we compute the optimal value function? That is very easy. So clearly, given Q star, you want to take the best action, not arbitrary action, and that is going to get you the optimal value. So that is straightforward. Then in the case of grid world example, let me give just one example very quickly. Think about this stage. This is the optimal value corresponding to that stage. Here I have marked all the Q value corresponding to that state and action. So given the state, you have 4 different actions: go up, go down, go left, go right. So the Q value corresponding to that state and go up is 0.77. then go right is 0.85, this is 0.57, 0.6 is. Clearly, you can see the relation between Q value and the value. The Q value corresponding to the best action is going to be your value function. Another important relation that you can observe here is that in this table, we have marked the optimal action also. It means that if you are in the state, it is optimal to go right. If you are in the state, it's optimal to go right. If you are in the state, optimal to go up. Okay? But it is not clear how we got that action. But if you are going to compute the Q value, it is very clear how to compute that action. So in each state, think about the 4 possible action, and then clearly you can see that the optimal action in each state is the action corresponding to the highest Q value. So this action, and this action, they have the highest Q value, and that is the optimal action according to this, according to this, and according to this. So that essentially answered one of the most important questions that we started with. How do we compute the optimal policy? That is, given the optimal Q function, the optimal policy is straightforward. That is, you just need to take the optimal Q function, take the argmax, and that will give you the optimal policy. Okay, so far we discussed the idea of like computing the optimal value function and optimal Q function and using that to compute the optimal policy. But that seems to be a roundabout way because our goal is to find the optimal policy. Is there a way to directly find the optimal policy? The answer is yes, and that approach is called policy iteration. So essentially, instead of iterating over the values, you want to iterate directly over the policy space to find the optimal policy. I'm not going to spend too much time about on this algorithm. It's a little more technically involved. So I'll just tell you about how to do this, and then later we will come back to this when we discuss about policy gradient algorithm. Algorithm is very simple. You start with an arbitrary policy pi node. Now you want to see how that policy is doing. How do we know that? You know how to do that. That is, at time step k, you have a policy pi k. You want to see how good that policy is. So you want to get the value corresponding to that policy. In this lecture, I didn't mention how do we evaluate the policy, but that is an approach very similar to value iteration. So if you want, you can look it up one of the reference. But the idea is that given a policy, you kind of estimate or evaluate how good that policy by computing the value function corresponding to that policy. Okay, now you are at time step, you are at iteration k, you have a policy pi k, you have the value corresponding to that policy pi k. Now you want to get the next policy pi k plus 1. How do you do that? Very easy. Your next policy is going to be the greedy improvement corresponding to the current policy. What does it mean? You already have the value corresponding to policy pi k. Now assume that you are in the state x and you take an action A, and from the next time onwards, you are going to follow the policy pi k. But now you don't want to take any arbitrary action. You want to take a greedy action. And so essentially, if you take the action corresponding to the best value on this left-hand side, that is going to be your next policy. So intuitively, what you are doing is that you are taking the greedy action at the current step and then following the policy pi k from the next step onwards. And then you are taking a greedy update to get pi k plus 1. You can repeat this iteration, and the result is that, or you can rigorously prove that the policy iteration will converge in finite number of steps. So why I'm emphasizing this idea of finite number of steps? Because value iteration converges is an asymptotic idea. We are saying that as k tends to infinity, value iteration will converge the optimal value function. Here I am arguing that it take only finite number of steps for this to converge. So ideally, this seems to be an easier way to compute the policy iteration, to compute the optimal policy. But the caveat is that this step is computationally intensive. Evaluating a policy to get the value, given a policy pi k, to get the value function is going to be computationally intensive. So even though it is converging in finite number of steps, in terms of the actual clock time, it may perform similar. Okay? So to state it more formally, the policy iteration, there exists a finite number k naught such that after some finite number of iteration, you already got the optimal policy. And then Bad news is that the finite number that I talked about can be very, very large. It can be exponentially large in terms of the number of steps, but in practice, it is much, much faster. Good. Okay, so let me summarize this part so far. So what are the things we discussed? Given a policy, how do you quantify how good that policy is? So you need to evaluate this policy. We didn't discuss this, but I just want to put it there. Our main goal is to compute the optimal value function. We discuss value iteration to do that. Then our goal is to compute the optimal policy. We discuss two approaches called value iteration and policy iteration to do that. This class of algorithms generally are called dynamic programming algorithms. Okay, so many of you may be familiar with dynamic programming algorithm from your algorithm class or control class, but given that this is at the core of reinforcement learning literature, I want to give like a kind of, I think I took around 30 minutes to do this, but I want to give that emphasis clearly. Okay. So before taking the break, let me quickly introduce what is coming next, and then we'll take like I'll announce the break and then we will reconvene. Okay, good. So what do we have so far? If we know a real world control problem, we know how to model that mathematically. Then we know how to solve that mathematical formalism using MDP and dynamic programming. We can compute the optimal value function and we can compute the optimal policy. So what remains to be done? Are we done? No, because so far we discussed computational approach. What do we mean by that? We assume that everything about the environment, the state of the environment or the model is known to us. In particular, we assume that we know the reward exactly. We assume that, more importantly, we assume that we know the transition probability metrics, which essentially mean that if you have a complicated plan that you want to control, drone, autonomous system, you know everything about the control dynamics and you know everything about how that interacts with the real world. In the case of autonomous car interacting with pedestrian, drones behaves in like wind or rain. So you assume that you know everything about the world. You can model that accurately. Given that model, you assume that you have a computation procedure to compute the optimal policy. Clearly, that doesn't make sense, right? There is no way you can model everything about the world or then the control system operates and then use that model to compute the optimal control policy, because it is too complex. Even if you assume that by so many observations you can model it, but the memory required for that will be huge. Even if you learn and compute a model, use that model to do dynamic programming is going to be very, very difficult, because dynamic programming is known to be an extremely difficult computational algorithm due to something called curse of dimensionality. So how do we solve this real world control problem? First, if you don't know the model and if you don't want to learn or compute and use the model, that approach is called reinforcement learning. So reinforcement learning is a learning version of solving control problem using the framework of dynamic programming or MDP. We are going to discuss two main classes of reinforcement learning algorithm. One is value learning algorithm. In particular, we'll discuss Q learning algorithm. You can think this as the learning equivalent of value iteration. The other class of algorithm is policy gradient algorithm. You can think them as the learning equivalent of the policy iteration algorithm. Okay? So let me emphasize this again. We know dynamic programming we can compute the optimal value function and optimal policy using value iteration or policy iteration. But the crucial assumption, the elephant in the room, or like the crazy difficult assumption that we often make when we solve dynamic programming is we know the system model. That is almost always not correct. So it is for if you are solving a very large control problem like a robotics, and then especially if you want to do some real world control task, assuming that you know the system model and you use it to solve dynamic programming, which is essentially most likely that assumption is invalid. Okay, so what is our goal? We want to address the same question. We want to come up with the same solution for the same question. We want to evaluate the policy. We want to compute the optimal value. We want to compute the optimal value function, and we want to compute the optimal policy. But we don't have a computation model now. because we don't know the system. So we are going to change the computation and computation part here to learning. So we want to answer this 3 questions, assuming that we don't know the rewards, we don't know the transition probability. What we have is, we have the observation of the sequence of states, action, and the reward. We are going to use this sequence of observation to learn the optimal value function or optimal policy. Okay, so I think I will stop here. Then we can resume at 3:30. So we have around 7 minutes break. If you have any questions, please type it in the chat box. Thank you. Those who are already familiar with Markov decision processes and dynamic programming, but I think that, as I mentioned, I thought that it is imperative that I should cover that aspect, because without that, the picture will be imperfect. But now we are going to the real core reinforcement learning algorithm. How do you learn to control an unknown system if you don't know the plan model or the system model? So here, we are going to discuss an algorithm called Q Learning. To make it more rigorous, I'm going to define a Bellman operator for the Q function. So recall, this is the Bellman operator for the value function that we discussed. So just like that, I can define a Bellman operator for the Q function. So F, you take the input Q, and then this is defined. You can see that it's almost the same. But there is one very important difference that you can notice. That is, in this Bellman operator for value function, you have a max outside and an expectation inside. In the Bellman operator for Q function, you have a max inside and the expectation is outside the max. Okay. Well, that seems to be like some small technical thing. And why does it matter? In the next slide, I will show you that that is essentially makes a whole lot of difference, and that fundamental difference, so that we can actually learn from sample without the requirement of a model. Okay. So before that, you can prove the similar thing about the Bellman operator Q, that is the monotone mapping, it's a contraction mapping, so there's an optimal Q star, blah, blah, blah. So all these technical details will hold through. So for the technically inclined people, you can get into the reference of this. Now, why do we need Q function? So we spend a lot of time on understanding the value function, computing the optimal value, using the optimal value to compute the optimal policy. But why can't we work with value function? Why do we need Q function? One obvious answer is that Q function is simple to compute the policy. Okay? Given the optimal Q function, all you need to take is argmax to compute the optimal policy. Given that our real objective is to come up with the optimal control policy for interesting control problem, robotics, autonomous driving, drone landing, given that that is our goal, and it may be better to learn the Q function so that you can immediately compute the optimal control policy. But there is one more fundamental aspect related to why we are interested in Q learning instead of why we are interested in the value learning. That is because obtaining unbiased samples corresponding to this FQ is much easier than obtaining unbiased samples of the Bellman TB. What do I mean by that? Consider the Bellman operator corresponding to Q function. It is written, this is the expression that we used, but that can be written in terms of an expectation. Think about this. What do we have here? We have the deterministic number, gamma times an expectation, and something is inside. Okay? So if you actually want to evaluate this expression, you need to evaluate this expectation. But for that, you need the transition probability matrix, which essentially means that you need the model. But you don't know the model. The only thing that you have is observation. Suppose you have the observation xt, at, and xt plus 1. The current state, current action, and the next state. So you don't know how to evaluate this expectation, but suppose you have just one sample of this quantity or one sample of this quantity without expectation. That is going to be r xt at plus gamma times max over b q of xt plus 1b. I just removed the expectation and I got one sample. Clearly, if you take the expectation of this quantity, you will get this quantity. So that is a property of unbiasedness. So the expectation of the sample is same as the true value, true expectation. But this is not true if you are using the Bellman operator corresponding to the value function. Why is that? There is a max outside. So here the max is inside the expectation. So that is still linear. But here, since this is max outside the expectation, you can see that max is here and this is expectation inside. That is no longer a linear operator. So one sample of the Bellman operator, that is max over A, R of xt at plus gamma V of xt plus 1, that is not an unbiased sample of this. If you take an expectation of this, you are not going to get back the Bellman operator corresponding to that. That is a fatal flaw because your goal is to essentially to learn from samples. So if you want to learn from samples, clearly value is not a good alternative to learn. You probably want to learn the Q function. So that is the main reason that we are shifting from value learning to Q learning. Now, without much delay, let me introduce Q learning algorithm without much technical details. We want to learn the optimal value function, optimal Q value function directly in a sequential manner. I'm going to assume that the action is taken according to something called a behavioral policy. Let me emphasize that behavioral policy is not the optimal policy. Suppose you have some arbitrary policy. That is, think about you have a simulation system, you are playing a game, you are in the grid world, you are taking control action arbitrarily. We are not assuming that you are taking control action according to an optimal policy. So for the rest of this slide, assume that you are taking control action according to a given behavioral policy. Q learning is a simple algorithm if you describe it in the following way. You initialize a behavioral policy, and then time t is equal to 0, you start, and then you assume that there is an initial stage. And this is an iterative algorithm. At each time step, you observe the current state st. Given the current state, you can take an action according to the behavioral policy. Then given the current state st and the current action, you will get a reward rt, and then you will get the next state st plus 1. You use this sample, current state, current action, the reward, and the next state to update your Q value as follows. Let me write this alpha as alpha t as a step size. Okay. So you are going to update your Q value at each time step. That is, your next Q value, your next Q value is going to be your current Q value plus a learning rate times the new observation that you got. Okay. So every time you have a new observation corresponding to the current state, current reward, and the next stage. So in fact, this is one RT plus gamma times, this is one sample, one new sample that you are getting, current reward, and then the next stage. And so essentially, this is one sample of that f of q that I introduced. You are subtracting the current value. So this is in a way, if you are familiar with control theory, this is something called the innovation that you are getting. That is the new information with respect to the current Q value that you have. So you update your current Q function by adding the new information or the innovation with a learning rate alpha. This is like a standard approach. Like if you are familiar with any kind of sample average approximation ideas or like control theory, adaptive control, or any kind of engineering system where you want to keep track of something, this is what you do. You update your new value as your current value plus a small multiplication factor, a learning rate alpha with the innovation. That is algorithm. So as you can see, the algorithm is very, very simple. You keep on taking the control action, you generate observation, you update your Q value. What will happen? Okay. This Q, you can show that under some condition, the Q learning algorithm will converge to the optimal Q function. That is, the condition are as follows. If all state action pairs are visited infinitely often, that's a very important assumption. I'll come back to that right now. And your learning rate satisfies something called Robbins-Monroe condition. What is Robbins-Monroe condition? The sum of the learning rate should be infinity. Sum of the learning rate square should be less than infinity. So learning rate should decay to 0. So if you have a sum of like an infinite series and that is less than infinity, means that your values are going to 0. So clearly you want your learning rate to go to 0, but you don't want the learning rate to go to 0 very fast. You want it to go to 0, but not very, very fast. So this condition essentially a balance between how fast your learning rate is going to 0. So under assumption 1 and assumption 2, or under condition 1 and condition 2, we can show that Q learning will converge. That is, Qt will converge to Q star almost surely. Let me read that theorem again. So if all state action pairs are visited infinitely often and step size satisfy Robbins-Monroe condition, that is, sum of the step size is equal to infinity and sum of the step size square is less than infinity, then the Q learning will converge to Q star almost surely. This is actually a very surprising result. I mean, it may not be obvious, and it may not be obvious why it is surprising. So when I studied this and the more I think about this, I realized that this is indeed a surprising result. Why is it surprising? We are arguing that there is an algorithm where you are taking arbitrary control action, and then by taking this arbitrary control action, you are essentially converging to the true Q function almost surely, even if you are taking action suboptimally according to a behavioral policy. So that requires, the proof of this algorithm requires non-trivial efforts. So the Q learning algorithm was first proposed in 1989, but they proposed this algorithm, Watkin and Diane proposed this algorithm, and then it became popular. But the first rigorous mathematical proof came around 1994 by two different parallel papers, like are published almost at the same time from MIT group, one from the machine learning group and other from the control group. So it took some time to understand or like come up with a rigorous mathematical techniques to analyze this algorithm. So even though the algorithm is very simple, I want to emphasize that if you want to do something more, you want to update, you want to come up with a better Q learning algorithm and show that it is converges correctly, that requires a non-trivial mathematical effort. It is using something called stochastic approximation results. Probably some of you are familiar with that. Okay. Now, let me emphasize again on this behavioral policy. Since you are not taking control action according to the optimal policy, or like not the optimal policy correspond to the Q function given to you, it can be any policy. This algorithm is called an off-policy learning algorithm. What do we mean by off-policy? That is, you are following a policy that is not exactly the optimal policy at any given time. So in principle, Q learning can be done in a supervised learning way. That is, I suppose I have a model, I generate like a sequence of like state, action, reward, next state, action, reward, next state data in an arbitrary manner in such a way that I satisfy this condition. All state action pairs are visited infinitely often. And then I give you this data. In principle, you can run Q learning algorithm on that data without interacting with the actual simulator by yourself and still compute the optimal Q function. Let me emphasize that is in principle. When you actually try to do that, this will have like a lot of difficulties. One active area of reinforcement learning is how do you do off-policy learning? How do you do off-policy learning efficiently and optimally by reducing the variance? It's a very, very active area of research. You will see a lot of papers in machine learning conferences now. Okay. Now, a few caveats that you need to be worried about. So we need to explore enough. That is, we need to make sure that the behavioral policy will visit all state action pairs infinitely often, and we need to use the correct learning rate. That is still any easier assumption. You can set the condition on the learning rate, but making sure that each state action pair is visited infinitely often according to your behavioral policy is a little bit tricky. So what is a typical behavioral policy that you use? Well, the most common behavioral policy is something called epsilon greedy policy. That is, given the Q function at step K, you take the greedy action. So, excuse me. This actually. Okay, given the Q function, you will take the greedy action A star, that is the action that maximizes the Q function with a high probability, but you don't take that always. With a small probability epsilon, you are going to take a random action. Okay? So that is a way that you are kind of exploring other action, essentially checking what will happen if you take other action. There may be a good outcome corresponding to that action, but you are not certain. So you don't want to put complete emphasis on some arbitrary action. You know that the greedy action A star will maximize your current Q function. So ideally you want to take that action very often, but at the same time, you don't want to completely stop exploration because you still don't know the system model. So this is the standard exploration policy that you will be using in Q learning algorithm. So when you read a Q learning paper, typically they mention that the policy they will be using is epsilon greedy. Okay. So under some condition on the transition, so this is also theoretically justified. Under some condition on the transition probability metrics, you can show that all state action pairs will be visited infinitely often. Now, we just proposed like one behavioral policy, that is epsilon greedy behavioral policy. Is this the best behavioral policy that you can take? Is this the best optimal online control policy? Or is not the best optimal? Is this the optimal online control policy? Well, to answer that question, we first need to clarify what do we mean by optimal online control policy, because we haven't defined like a precise objective according to which we are computing the optimality, right? Your optimality will be different. You probably want to balance exploration, exploitation, or you probably want to balance sample complexity, or you want to make sure that you explore in such a way that system is stable, or system is stable, or system is safe. You are not taking some action so that your drone will crash. So depending on your metric of performance, your online control policy will change. So that is another active area of research. How do you learn fast enough in such a way that you can reduce exploration versus exploitation trade-off, you can reduce the sample complexity, or you can run system safely, or you can ensure that system is stable. I'm not going to that active area of research, but I just want to mention that epsilon greedy is not always the best control policy that you can use. Okay. Good. With that kind of basic idea of Q learning, we are going to the deep Q learning approaches. Okay. So what is deep Q learning? Ideally, we want to come up with a reinforcement learning algorithm to solve large-scale problem. Large-scale problem means useful problems, right? So far we were thinking about a Markov decision processes model, MDP model. If you remember, I made an assumption that the number of state is finite and the number of action is finite. How good is a finite state model? In principle, the number of states in a backgammon model is finite, though that number is very, very large, 10 power 20. Some of you might have heard about the successful reinforcement learning algorithm from DeepMind, where they developed like a reinforcement learning algorithm to beat the human champion in the game of Go. The number of states in that is 10 power 170. That is clearly more than the number of atoms in the universe. So even though these things are finite, this is extremely, extremely large. But the Q learning algorithm that we just discussed, let me go back. this algorithm essentially assuming that you have a lookup table of Q function for all state and action. If you have 10 power 20 state, there is no way that you can store the Q function corresponding to all state and all action. You can forget about solving like a Go game where the number of state is 10 power 170, right? So how are we going to tackle that problem? Okay. And also think about the provable convergence guarantee for Q learning. The first and the most important convergence guarantee, the assumption is that your behavioral policy should visit each state and action pair infinitely often, which essentially means that if you have 10 power 20 state, you need to spend at least 10 power 20 time step to learn the system, which is again, it's not a feasible assumption to make. So what can we do? Can we use the current theory of reinforcement learning to solve this large scale problem? And that is where the deep Q learning comes in. Essentially, deep Q learning is nothing but Q learning with function approximation. So instead of representing the value function or Q function or policy in a tabular form as a lookup table, we are going to represent that using function approximation. Your function approximation, the most popular function approximation now you can use is neural network. So you're going to assume that your Q function is represented by a parameter W, where that W can be a neural network. So you have a neural network parameterized by W. You can give the current state and current action as the input, and the neural network will give you the Q value corresponding to the state and action. Intuitively, what is happening? This is essentially true for supervised learning. If you are using neural network, what we are seeing, what we are trying to do is that we are somehow trying to generalize the system from seen state to unseen states, right? So once you are using the data generated by the algorithm, you are kind of fitting a function, and that function is defined for each and every state of the system. So even though the algorithm or the agent hasn't visited those states before, this function approximation is giving an estimate about the value or the policy corresponding to that state. This is nothing specific about the reinforcement learning. This is true for the general neural network or like any kind of function approximation. Okay, so what do we need to do deep Q learning? Obviously, what we want to do is a good class of function approximators. If you have taken a machine learning class, you know that there are so many function approximators that are useful. You can do linear combination, decision tree, tile coding, Fourier basis, or like very powerful kernel called reproducing kernel Hilbert space. Well, I said all this beautiful function approximator, but we all know what is a function approximator that you're going to use. It's going to be neural networks because that is very popular, and then it is we know that it is powerful, though some of the technical details are still a mystery. Okay. Good function approximation is not good enough. You can have like the most powerful neural network with many deep layers, but if you don't have a good training algorithm, again, that is not useful. So so that we know from the history of deep learning itself, the current neural network structure and the architecture and the basic backpropagation algorithm is known in late 80s, but somehow it was not good enough. One is, of course, the computation difficulty, but more importantly, how do you effectively combine with smart gradient descent algorithm and other pre-processing and then hyperparameter tuning, etc., was kind of maturely developed in the last 5-6 years. That is one big reason for the amazing success of deep neural network. So good deep neural network is not good enough. Let me emphasize that. What we need is a good training algorithm to use neural network. And what is different from supervised learning? We have non-IAD data, and our data is non-stationary. So how do we do Q learning with function approximation? The equation, though the derivation is a little tricky, I'm kind of skipping over the technical details. This is how you do Q learning with function approximation. If you notice, this is exactly like kind of very similar to Q learning algorithm. Your next estimate, next parameter WT plus 1, which approximate your Q function network, is your current parameter plus the learning rate times the innovation that you are getting, the current reward plus gamma times the Q max over B, Q of ST plus 1B with W minus the current value. So far, this is exactly the similar, but now you have a new term, which is essentially the gradient of the Q function with respect to the parameter that you are using. Okay. So your algorithm is the following. The next parameter is the current parameter plus learning rate times the new information or innovation times the gradient of the current function. This you can do by backpropagation. Okay. Essentially, everything can be done by backpropagation. So, but this is the basic idea. Good. Now, does it converge? I mentioned that there is very sophisticated theory about convergence of Q learning in the tabular case, but unfortunately, not very surprisingly, there is no existing result which will rigorously show that Q learning with function approximation, as defined in the following way, will converge the optimal Q function. That is still an open area. In fact, there is a lot of counterexample that the Q learning, if you define in the following way, will not converge the optimal Q function. Even forget about neural network, even you are using linear function approximation, which is eminently analytically tractable. And even if you try to work out all the detailed maths, you can come up with simple counterexample that things will not work. Okay. Why that is happening? In one way, if you think about in terms of neural network, yes, neural networks are like complex object with locally so many local minima, so it may be complex. But here you see that even with linear function approximation, you are not getting any interesting result. Why that is possible? So Sutton and Berto, who are the authors of reinforcement learning textbook, the seminal textbook in this area, they call this as deadly triad. So what is really happening? In this Q learning with function approximation, it can be linear function approximation or kernel or like neural network. We are using three important ideas. We are using function approximation, obviously, because you are approximating your Q function with neural network or linear function. It's essentially a generalizing the values from seen to unseen. It is clear that you cannot do away with this because your control problem are typically very, very large. So you need to use function approximation. You are using something called bootstrapping. That is, look at this equation. Rather than training everything from the scratch, you are kind of currently using the existing estimate about the Q value to update the current Q value. So it is not that you are just taking the gradient alone. You are using this factor to kind of bootstrap your learning. It's a little more involved concept, but essentially, so I don't want to get into the details of that. But the intuition is that you are currently using you are essentially using your current estimate about your Q function to learn about the next estimate. A moment of thinking about this will tell you that this can go incredibly wrong. What you are doing, you are taking a current guess about the Q function, use that current guess to take the next action, and then use the next action or the data point to estimate your current guess, and then you update your guess and take the next action. Suppose if your current guess is wrong, then you are taking a wrong action to that current guess, then you are taking a further wrong action and a further wrong action. So it's very clear that if you are not doing bootstrapping correctly, it can get incredibly wrong. This is again a problem that is unique to reinforcement learning or control, because control is inherently involved taking sequence of decision. In supervised learning, this is kind of avoided because you are assuming that every time you are getting IAD data point. So even if you are making a mistake at a given time, probably that is not going to matter in the next time step. So bootstrapping and taking estimate based on the current guess is a very big issue. So 1, 2, and 3 is off-policy training. I mentioned that the Q learning algorithm is an off-policy learning. You are not using the current policy to generate data points. You are using a policy that is not the current best policy or the optimal policy. So that is essentially creating another issue, mainly due to the variance of the estimate. If you are trying to estimate a quantity from if you are trying to estimate a random variable, or you are trying to estimate the mean of a random variable, but the samples that you are getting is not according to the true distribution, then you need to take some kind of adjustment to convert the samples that you are getting to the distribution according to you want to estimate, then compute the estimate. Off-policy learning is similar to that. You are generating data points, your observation according to a given policy. So that will be coming according to a given distribution. But the real Q function that you want to estimate is totally different distribution. So there is a mismatch between this that leads to big issues related to variance. So Sutton and Berto mentioned that this is deadly triad. If you are trying to develop an algorithm that uses all these properties at the same time, then probably it is not it is not going to work. Okay? If you take away one of these three, then you can actually rigorously prove that that will work. You have rigorous convergence guarantees. So, well, it's an interesting observation, but in practice, we do this anyway, just like we do neural network. But if you do this very naively, it is not going to work. We need to address some very important issues that is arising in Q learning, especially due to the fact that we are trying to learn a dynamical system. There's a sequential nature involved. So next, I will present two interesting ideas on deep Q learning called replay buffer and target network. And I will tell you how that can be used to overcome some of the fundamental difficulties in Q learning. And then I will talk about the deep Q learning algorithm from DeepMind. Okay. So one fundamental issue in Q learning, by virtue of that it is trying to learn like a sequential, it is trying to generate data sequentially, is correlation and forgetting. Let's quickly recall Q learning. Q learning is essentially you take an action AI, then you generate a data point that is current state, current action, the reward, and the next stage. Then you update your parameter using the current data point. That is your Q learning, and then you repeat over this. What is the problem with this? As you can see, by definition of Q learning, the data is used in sequentially in the same way as they are observed. Okay? And you can see that the past data, however valuable that is, immediately discarded. You are never going back to that data. So every time you generate a data point, use that to update your parameter, discard it. So sequential nature and then forgetting the data. This leads to two important issues. One is the issue of correlation. Since the data is generated sequentially, these data points are strongly correlated. Now, remember, we are using function approximation, in particular neural networks, for approximating the Q function. If you even have like a brief familiarity with neural network, you know something called backpropagation, which is essentially a gradient descent approach to train neural network, which we'll use again here. And then you know about stochastic gradient descent also. Stochastic gradient descent is a very well studied area, and there is some very interesting result. Essentially, almost all those results assume that the data that you are getting is IID in nature. Okay? But in this case, clearly due to the sequential data, we are breaking one of the most fundamental assumptions that is required for the working of stochastic gradient descent algorithm, that is the data is IID. Another issue with this kind of sequential Q learning is the issue of rapid forgetting. So you may be getting some observation. Some observation may be really useful. Think about you are trying to learn an autonomous driving, come up with an autonomous driving algorithm, and then you generate data. Suppose some data points involve some kind of interaction between an autonomous driver and pedestrian, or like another car. You are driving your autonomous car, suddenly a car tries to overtake you, or pedestrian comes in front of you, and then the algorithm does something important so that there is safety is observed. That data is much more valuable than miles and miles of boring data that line following, right? But in this Q learning algorithm, that data will be used only once and then discarded. Clearly, that is not a good way of using the data with so much information. How are we going to address these two things? I'm going to address the first aspect, the correlation issue, in the following way. This idea is called experience replay. Okay? So what is experience replay? It is a method to break the temporal correlation by mixing more or less recent experience or the update and use the rare experience for more than just a single update. So the idea is very simple. We are trying to mimic supervised learning in some way. Assume that, so what you do is you will create a data bucket B, which I call replay buffer. So initially assume that you use some random policy, some arbitrary policies to generate data points. That is current state, current action, reward, and the next state. You generate a lot of data points and put all this data point into this bucket. Okay. Now you're going to mimic supervised learning, or like not supervised learning, kind of neural network stochastic gradient training in some way. That is, at each time step t, you sample a mini batch of data points from the replay buffer. Use this mini batch of data points from the replay buffer, sampled randomly. Let me emphasize that, sampled uniformly at random. Then use these data points to update your parameters. Okay? Then once you update, you can select an action according to epsilon greedy policy. You get a new data point and you can put that back to the replay buffer. How is it breaking that temporal correlation? Because we are putting all the previous data, not all the previous data, say past, say 1 million data point into a bucket. But rather than selecting just the previous data, I'm going to select, say, 128 data points, say uniformly at random. So the data that I'm selecting to update my parameter is coming not from the immediately previous samples. It can come from any sample from, say, t minus 1 million to t, the last 10 million time step window. Okay. So by doing this, what we are doing is that we are kind of breaking the sequential nature of the data with the hope that we are making this strong correlation assumption and making the data more look like an IAD data point rather than like a Markovian or strongly correlated data points. And also, it is also addressing this immediate forgetting idea. Since we are putting this data points into the replay buffer, you are sampling from the replay buffer, you may be using the same data point again and again. Of course, if you are uniformly sampling from this data point, then you are not using more important or more the data point with more information contained more often. So I will discuss that as a new strategy, but here assume that you are sampling the data points uniformly at random. This is the idea of experience replay. So it's clear that for experience replay to work, you need off-policy learning, because you are not updating your parameter based on your current control policy. You're almost mimicking supervised learning in this aspect only by sampling from a given data point. So that is an off-policy learning. So any algorithm will not work. You need an algorithm that will converge in an off-policy setting. But we know that Q learning is an off-policy learning algorithm. So Q learning can be used for this. Another important idea that we'll be using is something called target network. Okay, this is also an issue that we'll face by doing gradient descent. Think this Q learning update as a gradient descent update. Your new parameter is current parameter plus learning rate sometimes update. So this is that gradient term that you are multiplying with. Okay. If you think about this, you are essentially tracking this quantity, the quantity that I draw by the red line. So this is essentially the target for the gradient update. Your goal is to update the parameter W in such a way that this term is essentially tracking this term and you want to make that term 0. What is the problem with this? In supervised learning, your target is like some kind of softmax error based on the true ground truths. That doesn't depend on the parameter. That depends on the ground truth. But here, since you don't have supervised learning data point like given by the supervisor or label data, your target essentially depend on the parameter. So rather than this become not a gradient descent to a target, this is almost becoming a tracking problem. So if you have some familiarity with control literature, where you really need to track like a control signal or reference signal, you know that is much more difficult rather than keeping like a constant kind of level of control. So now this also violates an important assumption for gradient descent, where gradient descent is essentially kind of going to like a ground truth determined by the label, but here you are converting that to a tracking problem. This leads to a lot of instability issues. If you are trying to do gradient descent in this way, then your gradient descent, of course, kind of exhibits some kind of very unstable behavior, and this will lead to oscillation. Okay? So how do we overcome this issue? We introduce something called a target network to overcome this issue. What is the intuition? So we will change the Q learning equation like this. So instead of keeping the target parameters same as the current estimate, we will use two separate networks. We'll use a W minus and a W, and we'll use this W minus as the target, and then do many W updates, keeping this W minus the same. So kind of again mimicking like a stable gradient descent algorithm. So keeping W minus the same, you update W, and after every n step, you kind of update your W minus to the current W, but not in every time step, after like some few episodes. So that can stabilize the system. So two ideas that we'll be using: the idea of replay buffer and target network. Okay, how that is useful? I'm going to explain that in the context of deep Q network. This is a paper, this is based on a paper from Google DeepMind that came in 2015. So most of you may be aware with the 2012 paper by Professor Hinton and his group called AlexNet that kind of changed the landscape of supervised learning algorithm, especially for image classification tasks. So then there's a resurgence of using deep neural network for many applications. And then people started working on reinforcement learning using deep neural network. And this is one of the most successful early papers on using deep neural network for reinforcement learning application. So since this is a very popular paper, I thought that I will explain the idea of deep Q network using the framework of this paper. They developed something called deep Q network, and then they showed the performance on Atari game. Many of you might have played Atari game. The system's like this. So the state of the system is the image that you see on the screen, on your computer screen. So that is this is the dimension, and then you have color. Action is the joystick that you're controlling. The reward is the reward that you're getting on the screen, and your objective is essentially to win the game. Okay. They use function approximation. Of course, they use neural network. So kind of multi-layer neural network. They started with a few convolutional layers so that they can take the image, convert into the appropriate representation. They used a fully connected network, and then they output the Q value. They did some pre-processing. That's essentially kind of take the original data that is still a very large dimension object. You do a pre-processing to convert to 84 by 84 image. And rather than using just the current image, their state is defined as the 4 recent image. So the state size is this. And then architecture is essentially 3 convolutional neural network and 2 fully connected neural network. This is not really a deep neural network in the real sense of deep neural network like ResNet and then VCGNet that you see here. It's like a 5-layer, but still it does the magic. So this is the precise characterization. You have 3 convolutional neural network and then like a few fully connected neural network. One thing to notice is that they use the same neural network architecture and hyperparameter for all the 49 games. They did train for different games, but they didn't change the hyperparameters. Let me use this. Let me post and then show you a video how that works. So this is the algorithm from DeepMind, and then you're seeing like how that worked for like a breakout game. Let me emphasize that agent given the reinforcement learning algorithm, the only information that is the state, the image, and the screen. Reinforcement learning algorithm in the beginning doesn't know what an Atari game is, doesn't know how to play the game. So there is no domain knowledge. You are starting from the scratch, and your goal is to train a reinforcement learning algorithm to play this game effectively. So after 10 minutes of training, you can see that like, yeah, this is hitting back, not very well. It's kind of, if you're not really good at the game or if you're trying in the beginning, then this is how you kind of play the game. So it is failing in a lot of times, but it's not completely bad. You can see that it's trying some things and then learn. After 2 hours of training, it plays really well. Again, starting from scratch, it doesn't even know whether this is like there's a game exists. It just observes the screen and then the points. But you see that it is playing well, like probably you and I play, or some of you are really good at ADDI players. I don't know. But what happens after like 4 hours of training is something that they call it magic happen, but you see, I would call it something very interesting happen, that it's starting to kind of develop its own techniques. So it realized that probably digging a hole towards the end of this, digging kind of a tunnel at the end, it's a good strategy, because once you kind of created a tunnel, then you immediately win the game. Okay? So rather than kind of sticking to like some strategy and then kind of trying to get the maximum reward, you can see that it's almost like in this particular example, I don't want to make a big jump, but in this particular example, it's like humans trying to kind of experiment and learning a good strategy without like just stick to your current optimal strategy. It is trying to find a very good strategy and then trying to give in the game. So how did it work? So this graph will explain you the performance of their algorithm compared to the other algorithms, like in particular comparison with a human player, and then like a linear function based approximation. So what you see on the x-axis is like the score that I marked here. Roughly, you think you can take it as the ratio between DQN score and the human score. So the higher the score, that is the factor by which DQN is overperforming the human player. The human players are not random players. So I have like a little details here. I'm going to skip all those. Essentially, they hired like players who can play ADDI games really well, and then collected the data from the human agents. Then they played their game. This is like a single agent game, so they don't need to play each other. And then they they compared their score. They observed that in 29 about the 46 game, their algorithm is performing much better. And you see that the scale is like, sometimes it's very large. Like, so this is the line above which DQN algorithm is performing well, below which human agent is performing well. And you see that it goes up to like 600 times, or like 600,000 and 4,500. So the performance improvement is tremendous for this deep neural network based reinforcement learning algorithm, DQN algorithm, compared to really good human players. Okay. And then the gray line here indicates how good like a linear function approximation works. You see that linear function approximation seems to work sometime, but not good as the neural network based function approximation. A few more statistics, like what it took for them to train this. Training time, it is not small. They have to train for 50 million frames, around 38 days of games experience. They used a replay memory of 1 million frames, and then other, like they used RMS probe, then they did target network, discount factor, and then exploration. So you can see all these statistics from their papers. A quick comparison. In the beginning, I mentioned that neural networks is, so there are two things. So in the slide where I mentioned that what are the things that we need to do, we need good function approximation, which is neural network, and we need good algorithm. What happens if you don't have a good algorithm, but you just have a neural network? This is what happens. So this is essentially their algorithm's performance with neural network, but without replay buffer and without target network. For the game called Breakout, the score is 3.2. Now you can see what is the improvement that you get by no experience replay, but there is a target network. So you see that there's a small improvement, but you see that there's a big improvement in introducing the replay buffer and target network simultaneously. So without introducing the replay buffer, right? So target networks is important, but you see that breaking the temporal correlation using the data not just once, but more often, is essentially a key to improve the performance. And clearly, if you use both replay and the target at the same time, the score has improved from just 3.2 and 316. Both these numbers, let me emphasize, are based on neural network. So naive application of neural network is not enough. You need to understand what is happening in a reinforcement learning scenario to develop good algorithms. And the performance compared with linear network. So this essentially to explain the power of neural network. Clearly, you can improve from 3.0 to 316 by moving from linear function approximation to nonlinear function approximation neural network. Okay. Algorithm is very simple, and if you look at the code, I have given the link for the code. You can look at the code. Code is also very simple. Just that they took so much processing time or computation power. The code and algorithms are simple. Now, in the next few minutes, let me quickly go through some of the improvements or the DQN algorithm. A major improvement that we can think about is something called prioritized experience replay that they added later. So clearly, in the experience replay, you are breaking the temporal correlation. You are using the samples again and again. But if you are using samples uniformly, then you are not making use of the most informative sample efficiently. As I mentioned, some samples are much more useful. Like in an autonomous driving example, some samples are very useful, much more informative than the other samples. So how do we use that? Clearly, if you change the uniform sampling policy to something non-uniform, that kind of sample from this data point according to the surprise factor in a way. So you want to do some kind of prioritized sampling on how much you can learn from this data point. So how do you know that a sample is useful or not? There are many ways to do that. They use some particular approach called kind of surprising element, but there are other more systematic approach of using this entropy based algorithm to do that. But this is one obvious improvement that you can do. Then there are many other things like double DQN, which essentially overcome the maximization bias, dual in DQN, more clever exploration, more clever tracking, and essentially many things they can do. An interesting, so all these papers are from Google DeepMind. An interesting work that they did in 2018 is called Rainbow Algorithm, where they put together all these algorithms together, that basic DQN, and then all this improvement, and discuss like how their performance can be improved. This is it looks like. So the gray, so this is the x-axis is the millions of time frame. This is the performance compared to a human agent. Okay. So the gray line, which you can see here, is the basic DQN performance that we discussed. This curve is the rainbow, that is putting this all at the same time, but very cleverly. You can see that within like 7 million frames, this new algorithm achieved the best performance of the basic DQN. With 44 million frames, it achieved the best performance of all the other algorithms known at that time. And still this is increasing. It is not kind of stabilized even after 200 million time steps. Okay. They didn't stop with that. So as a preparation for this lecture, I was checking what are the new improvement that DeepMind did for this class of problem. So this is actually a blog post from DeepMind from like 1 week back. They released a new algorithm called Agent 57, which essentially does something very remarkable. In all the 57 Atari games, this algorithm is beating the human agent. If you go back like a few steps where I showed this, you see that all these games, human agents were performing better. There is some deep reason for that. That is, these are very difficult frame from an AI perspective, because the feedback that you are getting, the reward that you are getting, is so insufficient to learn the nature of the game. Especially this game here, Montezuma's Ravens, is kind of infamous for that. So it took like a lot of work from a big group of people to understand how do you learn from like sparse environments and to do perform. You can see that this is the basic DQN that we discussed. This is the improvement that we discussed. Then they started introducing the idea of memory, like just like human. You think you are playing a game, you have a memory how you played previous, probably you are playing some games. Those information, that memory is useful for some other games. So how do you use that memory? So they introduced that. They introduced some smart way of doing exploration. They used the idea of transfer learning using meta learning, and then combined everything. This is 2020 work on like Agent 57. It's interesting to read about that. Good. So that essentially concludes my discussion about Q learning algorithms. To summarize, Q learning is essentially you want to learn the optimal Q function. Given optimal Q function, you can compute the optimal policy by taking the argmax. So how do you learn the optimal Q function if you don't know the system model? That's a Q learning algorithm. We discussed the simple tabular version of Q learning algorithm, but we immediately realized that that won't scale to large scale problem. So how do we do Q learning with function approximation, especially with neural network? So we introduce a neural network based algorithm, which performs very, very poorly if you just do a naive implementation. We discussed two ideas in a little more detail, that is called experience replay and target network, to make it better. Then we discussed many improvement like smarter exploration, developing, etc., like just the names only. And then we saw that with all this improvement, kind of very, very efficient performance can be achieved with respect to human agents. So Q learning, if you connect this back to the dynamic programming approach that we discussed, Q learning is essentially a way to learn the value function, or a kind of you can think this as a learning version of the value iteration. But we discussed two main algorithms for dynamic programming. One is value iteration and the other is policy iteration. Value iteration is kind of roundabout way. You are computing the optimal value function and then you learn the optimal policy. But now, can we learn the optimal policy directly without learning the value function? So for that, we are going to discuss something called policy gradient algorithms. And that is for the next 20 minutes or so. I will discuss policy gradient algorithm, but I'll take a kind of half a minute's break now and then look for any questions. Okay, I'll continue. So in the last part of this workshop tutorial, I'm going to discuss policy gradient algorithm, which is the most active area of research in reinforcement learning now. Excuse me. There was a question, what metrics can be used to evaluate the performance of the model? What metrics can be used to evaluate the performance of the model? Question is slightly not clear. Are you trying to say that we are estimating the model and how do we estimate that correctly? Or are you asking, given an algorithm, how do we estimate the performance of the algorithm? If the question is that if you come up with a reinforcement learning algorithm and then how do you evaluate the performance of the algorithm, the natural way is to check the value corresponding to the algorithm. The higher the value, the better. Okay? So if you have a reinforcement learning algorithm that achieves the really high value, then that's a good algorithm. But as we say, the proof of the pudding is in the demonstration, because if you are really solving like a control algorithm, for example, if you have a toy car, robotic car that you want to use reinforcement learning to come up with a control policy. You have a robot in your lab, or in more daring application, you have self-driving car or like a drone, and you want to control it using reinforcement learning algorithm. You develop a good reinforcement learning algorithm and you kind of port that to the drone and see whether the drone is flying. If it is flying and as landing as expected, yes, you have a good control algorithm. If it is crashing, too bad, you have a very bad algorithm. Okay, so I'm going to the next aspect, policy gradient algorithm. Let me come back to, so the way that I think about reinforcement learning algorithm as a learning approach to answer these questions. Okay? How do we evaluate policy? How do you compute the optimal value function? How do we compute the learning policy? But now you can't compute, you need to learn. We just discussed how do we learn the optimal value function for Q using Q learning. Now we are going to address how do we learn the optimal policy directly without using the Q function. The approach is called policy gradient algorithm. What is the idea? So far, we were discussing about parameterizing the Q function. That is, your Q function is approximated by a neural network. So here we are going to assume that your policy is approximated by a neural network. So what is a policy? So this is a neural network with a parameter theta. And if you are giving the current state as the input, then it will have like, it will output the probability with respect you take the given action A, given that you are in the state S. Suppose you have this many number of action, the output of the neural network can be this, or you can just sample one. It can be a single output, but the essence is that if you give the current state as the input, then you should get the probability according to which you take the action as the output. Okay, so unlike the value, you are going to parameterize the policy here. Okay. Now, what is your objective? Our objective is, as before, you want to find the optimal policy pi star that maximizes V pi. So we are going to consider a policy parameterized by the neural network theta. So pi theta of SA. You can read this as pi theta of SA is the probability that you take an action A given that you are in state S. Now, to simplify, let me introduce another variable j of theta, which is nothing but the value of the policy pi theta. Okay, let's assume that your initial state is fixed. So j of theta is just a scalar, because you don't need to evaluate the value for each and every state. You are assuming that your initial state is fixed. So you are interested in this parameter j of theta, or in particular, this is your objective. You want to find the neural network parameter theta star that will maximize your objective function. Objective function is the value corresponding to the policy pi theta. The theta is a neural network which parameterizes the policy. Okay. So how do we parameterize a policy? It is not too difficult. So for example, you can, if you are familiar with neural network, you know how softmax work. For example, in a classification problem, you have 10 classes, then your neural network has 10 output. Each output will suggest what is the probability that your input test image belongs to that class. You can think in the same way. You have 10 action. You can come up with a softmax kind of parameterization using this linear function approximation. For each action, fix an A, fix an S. For each action, you will get a probability according to which you take that action. So very similar. So what will happen if you have infinite number of action? Consider, suppose you have an LQG system. Your control action is continuous, right? So that means that you have infinite number of action. That can be effectively modeled. Like you can just assume that your neural network is estimating the mean and variance of your control policy. That is, your control action A at any given time is a noisy action with a mean with a parameter theta and a variance that can also be parameterized. Okay. So you see that this framework is very general. So unlike Q learning, which can deal only with finite number of action, this framework can deal with continuous action space. So that is one of the main reason that we are interested in policy gradient algorithm. And that is one of the main reason that the active area of reinforcement learning is mainly focused around policy gradient now. Because if you think about like more interesting real world application like robotics, the control action space is continuous. You have like a very large number of control action. So if you do Q learning can handle like maximum like a problem with like maximum 20 or 100 action to the max. Okay, it can approximate like a value function using neural network, but it still can deal only with finite number of actions. So if you have continuous action space, policy gradient is approach to take. Okay. So what is policy gradient? Intuition is very simple. You have a policy parameter theta. You want to do gradient ascent. That is, you have for a parameter theta, j of theta is your value. Then essentially you want to update your parameter such that theta is theta plus learning rate times gradient of j of theta. Very simple. Okay. This is a standard gradient ascent approach. Then what is so interesting about this? If this is the only thing that you are doing, so obviously the question is that will it converge? That's more involved question, because we know that if you are using neural network, the issue of convergence is kind of little fuzzy depending on the approximation. But here more important issue is how do we estimate this gradient? So we know that this is the right thing to do, but we need to know the gradient of j of theta. We can estimate the gradient of j of theta if we know the model, but can you estimate the gradient of j of theta efficiently from the sample? Good illusion about policy, then it is very easy to kind of impart that intuition into your neural network formulation so that you can parameterize well that policy so that you can learn that policy efficiently. Okay? That is especially useful if your policy action space is continuous or if your state space is very high dimensional, because you already have like a good characterization of the policy and then you can make use of this. Those who are familiar with control literature may immediately understand this. For example, you know something called linear quadratic Gaussian system, which is like a continuous states, continuous action system. It can be very high dimensional, but the control policy is very, very simple. Control policy is linear. Okay? So if you already know that the control policy has some specific structure, then you can exploit that information to learn faster. Okay? That is why robotics application, the most popular algorithm is policy gradient, not Q learning algorithm. There are some disadvantages. Convergence is one issue, but that is common with many neural networks. One disadvantage is going to be policy gradient algorithms are known to be extremely like high variance. So an active research area is to come up with algorithm with reducing the variance. Okay, so why this is difficult? Like the intuition is very straightforward, right? This is what you want to do. This is what you want to do, but why this is difficult? It's a little abstract. Let me try to explain that. The value of the policy, j of theta, will depend on two things. It will obviously depend on the policy, that is the immediate action that you are taking, but it's also going to depend on the stationary distribution of the state resulting from the policy. What does it mean? You are taking control action according to some policy. So the policy will determine what are the states that you are going to visit again and again. So if you are familiar with Markov chain, this is corresponding to the stationary distribution of that Markov chain, where the Markov chain is the Markov chain induced by this policy on that MD. So the reward depends on the policy in two indirect ways. One is directly the reward will depend on the policy. Then indirectly, the policy will influence the stationary distribution, and that stationary distribution will influence the reward. Okay? It is the second aspect that is very difficult to handle, because given the policy, think about the policy as the neural network, then it is very easy to compute the gradient of the policy. This is nothing but the back propagation. This you can compute. But given the policy, the stationary distribution or the gradient of the stationary distribution is almost impossible to compute. Why? Because the stationary distribution will depend on the transition probability. We don't know the transition probability, so we cannot compute the stationary distribution. And okay, if you don't want to compute, can we estimate this? That is very, very difficult. If you are familiar with Markov chain, you know that estimating the stationary distribution is essentially generating a long sequence of trajectory, wait long enough, and estimate the stationary distribution. So that is the crucial weakness of this approach. That is, if your reward depends not only your current policy, but also the stationary distribution induced by your policy, then that is very difficult to handle. So how do we estimate the gradient? That is why this theorem called policy gradient theorem, which kind of came around the same time from multiple groups, made a big breakthrough in reinforcement learning algorithm. So this is a little dense. So let me try to parse this. For infinite horizon discounted MDP, that is our setting. The gradient is written like this: sum over S, mu pi theta of S, sum over A, q pi theta of SA, and gradient of pi theta of SA. What is mu pi theta of SA? Mu pi theta of SA is the sum of, essentially it is equal. Suppose if you don't have the discount factor here, then it's essentially the probability that you are visiting the state S at time 1, time 2, time 3, and then if you sum all the probabilities, it is essentially that the probability that you are visiting the state S. You are adding the discount factor because you are kind of discounting the future state. So this mu pi theta of S is essentially nothing but the kind of representation of your stationary distribution in the discounted scenario. So from now onwards, I'm going to treat this as a stationary distribution induced by the policy mu pi theta. Okay. So now, given that representation, I can write this more efficiently like this. Okay. So gradient of j of theta is an expectation where my state is sampled according to the stationary distribution. Action is sampled according to the policy of this quantity inside the bracket. What is that quantity? Pi theta, q pi theta, my q value, and gradient of log pi theta. How do we go from here to here? That is easy, but I'm not going to the technical details. But you see that what is inside that bracket. You don't see a term that is gradient of mu pi theta there. Earlier, I was arguing that intuitively it should depend on this quantity. But here, when we formulate the problem in the following way, the gradient of j of theta is not depending on the gradient of the stationary distribution. That is a remarkable aspect about this formulation or about this theorem, which essentially overcome one of the biggest challenge in doing policy gradient. You don't need to estimate the gradient of the stationary distribution with respect to the parameter of the policy. So now your gradient is nothing but this. I can more efficiently represent like this. Okay? So this is the equation that I'm going to use for my policy gradient theorem: expectation of q pi theta and log q pi theta. Okay? So q pi theta is nothing but the value, q value corresponding to the policy pi theta, and this is gradient of log pi theta. Pi theta is my policy representation. Okay? Now we have the gradient. So this is when you know exactly how to evaluate this. But we know how to estimate q pi theta. This can be estimated from the sample. This can be done by backpropagation of your policy parameter networks. So to emphasize, so this policy gradient, this theorem essentially shows that it doesn't depend on the gradient of the stationary distribution induced by the policy, and hence it can be estimated from the sample trajectories. But when you read the literature, policy gradient theorem is a common terminology, but you will more often see something called actor critique. What is actor critique? Look at the policy gradient. Inside the gradient, to do the gradient, you need two quantities. You need the q value and this. This is something you already know because that is your policy parameter. You need to estimate the q value. Okay. So, but here I have written q value as if I have a tabular representation of the q value. But we know that it is impossible to do a tabular representation if you have a continuous states or continuous action. So you want to represent your q value again using a neural network. So you need two neural networks. One is a W neural network, where W is the parameter for the q value, and a theta neural network, where the theta is the parameter for the policy. Now let's assume that you can approximate the q function with respect to another neural network. Then you can approximate the gradient by replacing this q pi theta by a qw. Okay. Then qw is something that you can estimate, and then you can do the update. Theta is theta plus alpha times qw times gradient of log pi theta. You are removing this expectation, take the samples and do the gradient descent. Okay. We can do this, but now the question is, what is the W that I want to use? So I just gave you an update of theta without mentioning anything about W. So which W I should use? Intuitively, this W that I'm going to use should be a good approximation about Q pi theta. So the neural network corresponding to Q function approximation should approximate the Q value corresponding to the policy pi theta correctly. But how do we do that? Q pi theta is unknown, so we need to learn W, but theta is changing, so W should also change with theta. Okay? So that is where the idea of actor critic comes. This is the gradient descent that you want to do. Inside there is two neural network parameters, QW and pi theta. So you have a critic and actor step. A critic is essentially something that learns the Q value or the parameter W. That's essentially the Q value corresponding to the policy pi theta. So the intuition is that the critic is essentially learning the quality of the policy pi theta by computing or learning the Q value corresponding to that policy pi theta. Then it is giving a critic to the actor. Actor is the policy which is taking the action, that is why it is actor. Then given the critic input QW, it can update the theta value to update the policy parameter theta, and then it can improve the policy in the direction suggested by the critic. So combining this critic and actor, you get an actor critic network. Okay. So how do we implement a critic? This can be done by an algorithm called TD learning. I haven't talked about that here, but you can refer from one of these reference. But the idea remains the same. In actor critic algorithm is an efficient implementation of policy gradient algorithm, where you simultaneously estimate the Q value and update the policy parameter. Algorithm is simple. You update the policy parameter, then you sample the next state, take the next action, use that, estimate the value of the policy, and then you update the W parameter that estimate the Q function. The learning rate for theta is alpha theta. Learning rate for W is alpha W. If you are familiar with stochastic approximation, you know that the learning rate, this alpha theta and alpha W cannot be the same. That have to be adjusted appropriately for appropriate learning. Okay, I'll skip this slide in the interest of time. Okay, so we just introduced the basics of policy gradient algorithm. That is like a very basic implementation. For many difficult control algorithm, it will not work. So there is some, as I mentioned, this is an active area of research. So two most popular policy gradient algorithms are this trust region policy optimization and proximal policy optimization. These are almost available as software package now. You can install one of the RL toolbox and call this as function. In particular, this seems to be very popular. These are some of the things that you can do with PPO. You can see the half cheetah. This is trained by my PhD student Ryan, who is working on this kind of class of problem. Essentially, you assume, so this is from a Mujoko simulator. You can train kind of a robotic control task using PPO. You can train an ant to walk. You can train like a hopper. If you have a one-legged robot, can it kind of hop, and then try to kind of cross like a field? Yes. So if you have taken like a few mechanical engineering class, you will understand this is an incredibly difficult problem, especially if you don't know the model. It seems that by policy gradient algorithm, at least in simulation, we are able to do that. How do you convert from simulation world to real world is another different matter. It is possible. If you remember the example that I began with, the Rubik's Cube, robot hand solving Rubik's Cube, what they did was they simulated like they did a lot of simulation, and then they do something called policy domain randomization to go from the simulation world to the real world. Okay. Now, in the next two slides, I will conclude this short tutorial. This is a quick taxonomy of like RL algorithm. RL algorithm can be broadly classified as model-free RL algorithm and model-based RL algorithm. In today's lecture, I talked only about model-free RL algorithm. There's a lot of interest in model-based RL algorithm. Why? Because if you are a robotics person, you are like a car. If you are like a car company, you have like detailed models available. So there is no point in throwing away the model completely. You should be able to make use of some model. So how do we do that? That is an active area of research. I haven't discussed that. Today, we focused our discussion on model-free RL. We discussed value-based algorithm kind of Q learning. You can see that there are many different versions of Q learning algorithm. And then the policy gradient algorithm, you can see that there are many versions of policy gradient algorithms. So in conclusion, reinforcement learning provides a general purpose framework for AI. Because this can be solved as an end-to-end deep learning problems. And in particular, you can see that the intuitive goal of AI is to solve interesting control problem that appears in everyday life. And to solve control problem, you need a machine learning approach called reinforcement learning. So one framework that reinforcement learning researcher proposes is that reinforcement learning with deep learning, kind of a basic formulation of AI. Okay, so we just give like a very superficial kind of keyword-based introduction to, we did a very basic superficial keyword-based introduction to RL, but needless to say, like machine learning, RL is a very active research area. Let me give you like some qualitative question. One hot area in RL, like you didn't ask me this question during the break, RL is infamous for being data hungry. So how do you make RL fast is a very active area of research. How do you learn safely is another important problem. This is not something that you face in supervised learning, for example. You don't want your drone to crash during training or testing. So you want to learn safely. How do we use memory for transfer learning or meta learning? Because you know that human agents are really good at using a memory. Because even if you have like a rare experience, that will be used for learning other tasks. You do one task, that learned experience will be useful for learning other tasks. How do you incorporate that idea of memory for transfer learning and meta learning? How do you represent and learn hierarchical features? Again, human agents are really good at it. So you want to go from ETB to Weiss-Baker or like MSc, you are not going to describe the action to somebody else. You step down here from chair, climb down 13 steps, take a right, and then go through the road, etc. You are first giving the broad direction. Go from here, go to Weiss-Baker, go to engineering code, go to that square, and you reach MSc, right? Then once you give the hierarchical, the bigger picture, then you go down. How do you go from ETB to Weiss-Baker? So that is the next level task. But how do you climb down the steps? That's another layer of task. So human agents are really good at solving problem in a very hierarchical way, but RL is not good at it. RL will try to solve this problem entirely as a very big control problem. That's why it is RL is not successful in solving this class of control problem. So how do we introduce hierarchical features? How do we learn from expert? For example, I am a human agent. I know how to drive. If I generate kind of a lot of data point, how to drive efficiently in crowded streets, can I use this data with reinforcement learning so that I can learn efficiently from this demonstrated data? Clearly, demonstration of expert trajectories on how to maneuver your car in a crowded environment is extremely useful. So how do we use that? Still, RL, this is a very active area of research called imitation learning. How do we learn from multiple agents is another question, because you need to think about the issue of coordination, communication, issue of rationality, selfishness. A lot of game theory comes here. And so these are some very active area of research. So if you are interested in doing some cool research on RL, send me an email. So I'll stop it here. Thank you very much.
Thank you very much, Dileep. Any questions to the speaker? I think it's a long afternoon already, so probably